For our project, we decided to do a self-driving robot, using a robot that some of our team members already had and a pre-constructed track that had a black background and white lines. Our task was to get the robot to detect these lines and navigate effectively within them. The image came in from the camera and had a lot of other artifacts and stuff in the background. It was first converted to grayscale, and you can see what the camera view looks like in the video. To reduce the image down to lines and remove some of this extraneous data, the image was thresholded and binarized to create a matrix of either 1 or 0 for each pixel. Then a line of pixels near the middle of the image was chosen. This can be seen on the blue line in the following video. The line widths along this line were counted, using the pixels with a value of 1. In the ideal case, this is a simple process since the two groups of white represent the two lines, but in a non-ideal or extreme case, the robot may be positioned such that only one line is visible, as seen below. To handle this, additional logic was added to flag if it was only a singular line. If this was true, the line width value is correctly assigned to either the left or the right line. If it was not flagged, then the current line widths were kept the same. Based on this information, a steering value was collected. To smooth out these control values, PID was implemented.
Here's a comparison of both our PID and non-PID implementations. For our PID implementation, we first computed the line width using our computer vision model. We then took the average of this as well as the other values in the circular buffer and then fed this to the PID controller. The output of the PID controller was then set as the PWM steering value. For correct implementation, we had to experiment with the PID values as well as the buffer width.
A higher speed demo of our project can be seen in the following video. And now for some next steps to improve the project at a later point.
So this is the code we use to train a proof of concept machine learning model to recognize stop signs in the environment as the car is driving around the track. It just uses a simple TensorFlow model trained on a data set that we collected ourselves by running the car around the track and taking images labeled either containing a stop sign or not containing a stop sign. So what we do is we go through this data, we just pull all the data into one array that can be trained on, split it into a training test set, use a simple densely connected neural network. No need for convolutions or anything like this. This is a relatively simple problem, and we like to keep the computational complexity on the simple side. Go ahead and compile the model, train it. It trains extraordinarily quickly here on the Hypergator platform using the state-of-the-art A100 GPU. So here's the network after 100 epochs of training. We evaluate on the test step, and here we're able to get 98.6% classification accuracy.
Next part is about the neural network controller. First, we show the classification model trained by TensorFlow, and the image in the left in grayscale is the real image we processed, and it can run stably. Next part is the classification and regression model using PyTorch. In classification model, we make 30 discrete action space. We can see that it is combined with the throttle and steering. The structure of the network is nearly the same. They are consist with 2 convolutional layers and 2 max pool layers with 3 fully connected layers. The only difference is that the final output neuron is different because the discrete need 30 neurons and the regression only need 1 neuron to control the steering. Here's a video of the regression model. It will make some mistakes, so when using safety evaluation to evaluate the performance of each controller. The final part is about the risk verification. We use VAE model to monitor the difference of the MSE function in the reconstruction. So if